Hello and welcome to 6.3, and that will be Riemann sums, summation notation, and definite integral notation. Today we're going to be talking about basically that and kind of like an intro to summation notation, which is we'll get onto that in a bit. So first, let's just recap over Riemann sums, and let's just go ahead. Create a Riemann sum with n subintervals and have n be an infinite amount. So here, as you can see, it's kind of very hard to do that. Riemann sums work on the assumption. I'm just going to change my color to red. Work on the assumption that you have a definite amount. Okay, and that's easy when you're doing a certain number of intervals, which are a certain size. How though would you do a subinterval if it's an infinite amount? You would just have like an infinite amount of tiny rectangles, be it from the right or the left, and they just infinitely, a, like if you're shading the graph, and they're just going to be infinitely small and infinite rectangles that just keep going on and on and on and on and over and under the graph, just everywhere. And it's very hard. It's not impossible, but it's incredibly hard to calculate this using the Riemann sums. Because of this, we're gonna find a different way to do it. But we have to keep talking about it. So if n is the number of subintervals, rectangles on the interval a to b, what is the width of each subinterval rectangle? That would be b minus a over n. So the initial, whatever amount you're starting by, this initial minus this final. Final minus initial over n, which is equal to the change in x, which would be in a rectangle. This would be the base. That's the change in x. So if n goes infinity on the interval a to b, what does the width of each subinterval rectangle approach? That means that the change of x would equal to b minus a, let's say just b minus a over infinity. And we know that any number of infinity, it's undefined. There's just no width. Okay, a number defined by infinity equals basically 0, and since you can't have a width of 0, it kind of doesn't exist. It's really hard to do it this way. However, the sum of all these, collective areas would be the exact area beneath the curve, because it would just be the exact line where the function reaches and goes immediately back down. It would be basically no width. It just show you what you need. So in order to do it, we use different types of notations. One notation is the definite integral notation, and we write it called, we say that lim sigma, the limit sigma as n approaches infinity. Sorry, it's kind of my first time writing this. Infinity over n as k, when k is equal to 1. B minus a, this would be the base. B minus a over n. This kind of helps us to approximate, not approximate, but kind of approximate how many rectangles and until when times f of function of a plus b minus a over n times k, and this would be this is the width, and this is the height. This width, this is height. Now another way to write this is integral of, I think it was b and a of f of x d of x. These two mean the same thing. It's kind of just a simplified way, and we'll learn more about it. But this is basically how to use this, kind of like using Riemann sums, using using summation notation, Riemann sums, and definite integral notation, kind of like the basics of it. That's everything for today. For 6.3, Riemann sums, summation notation, and definite integral notation. Yeah, I'll see you in another one.